if you had the not perfect insulator. Two things, by the way. Not perfect insulator, and if you had the time.
Yeah.
It'll probably take a while for that to happen. But in sort of a broad sense, yes is the answer to your question. All right. Well, having talked about that, having mentioned that one word, and I mean in particular a reversible process, then I want to start talking about something near and dear to your hearts. That is the way your automobile functions. The typical internal combustion engine in service in the world today will be modeled on a PV diagram. Let me put the PV diagram right here. Some of you probably know how the system works. Others of you don't know how it works. And it doesn't matter whether you know or not. I'm going to explain it as best I can. Here's what happens. Here's how an automobile works. How an automobile engine works. Not in detail. The first thing that happens is you've got a piston in a cylinder, and on top of the cylinder, it's a closed cylinder with two little doors, which they call valves. Two little doors, and we're going to start with the doors closed and the piston at the top. So we're going to have a system. I'm going to turn it upside down because they always draw it the other way around. So we've got the piston in the cylinder like this. Piston, the rod attached to the rings to seal it. It's got a seal here, and it's got these two doors, which right now are closed. They're called valves. And what we're going to do is we're going to open one valve. We're going to allow one valve to open and let the piston go down. In so doing, it draws in a fuel-air mixture at ambient pressure. So as this piston moves down, what we do is we draw in fuel and air at a specific pressure. So we start in here at this volume, whatever the initial volume is, and we ended up over here at this volume, but it all happened at ambient pressure, at whatever the pressure is here at the valve. So it is an isobaric process from point A to point B. Once the piston gets all the way down, then this door closes again, and now you have a sealed chamber. The next thing that happens is now the piston moves back up again, compressing the mixture, compressing the fuel-air mixture. So, do I have blue up here anywhere? I have green. I guess I'll use brown and blue. They both start with B. So now I'm compressing this thing, and a key issue, ladies and gentlemen, is it's happening quickly. And when I use that term, I bet you remember what that means. It's not an isobaric process. It's not an isochoric process. It's not an isothermal process, but it's like it's adiabatic. It happens so quick there's no time for heat transfer. So this movement from position B to position C is an adiabat. So we get here along an adiabat. Now, once you've got the piston back up to its minimum volume, the doors are still closed, that's when the spark plug sparks. Oh, we got to do that in red, don't we? Got to do that in red. So, we get the spark plug sparking at that point, igniting the fuel-air mixture. And as far as we're concerned, what we're doing is simply releasing chemical potential energy. When you drew in the fuel-air mixture, you were drawing in air and gasoline, or diesel fuel. And that molecule, the gasoline molecule, has chemical potential energy. When you ignite it, when you burn it, you release that chemical potential energy. So, as a just sort of as a crude approximation, the piston is right at the top and you instantly release all of the chemical potential energy. That's going to do one thing, raise the pressure dramatically. So we have an isobaric, we have an isochoric rise in pressure from point C to point D, where the piston, a huge increase in pressure forces the piston down quickly through another adiabatic process, all the way down to its maximum volume. So we have another adiabat coming down like this to point E. Where the other door opens and allows out the excess pressure and lowers, again, in an isochoric way, back down to the initial ambient pressure. Then with that door still open, the piston comes back up, forcing out the spent mixture, the fuel-air mixture that's already been used up. This door closes, and it starts all over again. So, you take in fuel air, compress fuel air, release the chemical potential, do the work, release the excess pressure, get rid of the fuel air that's already been used up, and start over again. This is a cycle that describes, generally speaking, it describes the operation of an automobile engine or any kind of internal combustion engine that we have today, save turbines. Yes?
On this graph from E to B.
From E to B?
That's the released, the chemicals that you didn't use. Is that, could you use that part to describe how efficient the fuel was, how much fuel was converted into energy?
Yes, and we're about to do that. The key word that you use there is efficiency, and we're heading towards a formula for the efficiency of the system, and it is going to involve that. Yes. Okay. So this is a cycle that describes the typical. Oh, I should have put this on here because when we get to B, then we compress it all and we get back to A, but they call that F. So from A out and from B back, it gets back to F. A and F are the same point. That's where it all starts all over again. And like I say, this describes the efficiency. This describes the operation of your typical internal combustion engine, which of course is a story near and dear to our hearts right now. If you want to talk about a place where engineering needs to be done, it's to improve the efficiency here. Want to talk in practical terms? Fuel is getting ever more expensive. It's becoming rare, and we've got to use it efficiently. We can't waste it like we used to in the good old days. So, this cycle, which is called the Otto cycle, not like automobile, but a German name, Otto, O-T-T-O. The Otto cycle, O-T-T-O, is a pretty good approximation to what real engines are like. And the first thing we want to do is to determine the efficiency in an Otto cycle. Once we determine the efficiency, like good physicists, we'll look at the equation itself and try to figure out how can we boost the efficiency. That's how you do these things. You make a description, you do the physics, and then once you finish the physics and you've gotten the terms up there, then as engineers you say, how do I engineer a better solution? How do I make it better? And this is one area where those of you that get involved in this world, you're going to have a lot of possible employment doing things like that. So let's start talking about the efficiency. First definition of efficiency is simply, does this make sense? How much work you get for how much energy goes in. If you get the same amount of if you get the same amount of work out as energy you put in, you got 100% efficient, don't you? And as you might imagine, we don't. In a cycle like this, we do not get out all of the energy that we put in. In fact, she's quite right. This right here shows you one of the places where you're actually throwing away energy. This little E to B here, this little green one stroke right there. That's thrown out energy. That's energy that's thrown away. This chemical potential energy and that energy is the two places where we're really going to concentrate our work. So the efficiency, definition, did I write it down? I didn't yet. Definition, efficiency is going to be called E, is going to be work out divided by heat in. And the first one that's easy to get is the heat in. Q in is going to be the easy one to get. Heat in Q in is going to be, of course, C to D. Q in is going to be Q, C to D. That's where we release the chemical potential energy and convert it into thermal energy. That's what the spark plug and the burning of the fuel is all about. And of course, it is an isochoric process, isn't it? That happened right at the top. The spark plug ignites it, the whole thing raises pressure, so it's an isochoric process. M, C sub V, delta T, C D. So that's the easy one right there. M, C sub V, because it is isochoric, times delta T, the temperature change that we experienced when we went from point C to point D like that. So that becomes the key issue. This pen is running out of ink. Is there another black one back there? Is that one black?
There is a blue one.
There's the blue one. No, I don't need the blue one now. I need another black one. I guess I'll convert to brown, huh? You'll forgive me. Oh. Another black one. Just has a brown top on it. So we need to get this. Let's see, hope this one works better. Delta T. Oh, that's much better. C to D. That becomes the question. And it's really pretty easy to do because, of course, you recall PV equals NKT. Hence, therefore, T at D is going to be P at D, V at D divided by NK. Obviously, then, T at C, yes, is going to equal PCVC divided by NK. So now we've got it. We've got that delta T CD is the higher temperature, the final temperature, which is P D V D divided by NK minus the lower temperature, which is PCVC NK, like that. I would like to write that as PD minus PC times VC, divided by NK. Hey, wait a minute, what happened there? Funky algebra? Actually, no. It's not funky algebra, is it? What happened? What I did was just simply call VD VC. Is that fair? Yes, it's isochoric. The volume at C and the volume at D are identical to each other, so please don't get heartburn over that. Yes?
For the PV equals NKT for temperature D, temperature C, we reach temperature C via an adiabatic process. So
right.
Don't we want to use the adiabatic formula for that one?
No, because we're not talking about how we got from B to C. We're talking about from C to D. So whatever T at C is, we're only interested in going from there to there. We're not at this moment interested here because there is no heat flow here. We're only talking about heat flow in. So we're restricting ourselves to heat
But
flow
there
in.
is a temperature change, so if we were to calculate the temperature change from B to C,